Thank you for having me here. Argumentation has recently gotten increased attention within artificial intelligence. It is not only because of its crucial importance in AI, also because of its importance in and because of the application of argumentation in other fields of science like philosophy, medicine, and law. Argumentation can be assumed as a discussion among two or more people who have different point of view about the subject, but they are willing to find the truth via argumentation. And each argument presents a belief or a justification. So there exists a number of formalisms for argumentation. One of them, which is widely used and studied, presented by Dung, and it's called AFs for short. The structure of AFs are very simple. There are nothing more than a directed graph in which node present arguments and links shows the attack relation between arguments. The main power of AFs are behind the semantics of AFs. Each semantic clarifies under which condition arguments can be accepted. And semantics usually presented by extensions, and each extension is a set of jointly accepted arguments. Here you see the formal definition of grounded extension. I'm not going to present the formal definition, but the intuition behind the grounded extension is that the grounded extension collects all the arguments which are unattacked and the one that can be defended by these arguments. For instance, the grounded extension of this AF contains A, C, D, and F. This type of semantic has a special importance in this field because no one has any doubt on the acceptance of the arguments which are presented in the grounded extension. And each AF has exactly a grounded extension. Then it is important for us to study whether an argument is in the grounded extension or not. It is possible to construct the grounded extension and answer this credulous decision problem. There is still another type of semantics has been introduced for AFs to answer the credulous decision problem on their grounded semantics. For instance, if we want to know whether C is in the grounded extension, we really do not need any further information about the acceptance of D and F. It is enough to know that A can support C against the attack of B. Therefore, the set contains A and C is one of the strongly admissible extension of these AFs. This notion is introduced recursively over the parents of the argument in question. Although AFs are widely used and studied, it has a limitation that it is not possible to present any further type of links between arguments. Therefore, a number of formalisms have been introduced for AFs. One of the powerful generalization of AFs called abstract dialectical frameworks introduced by Verbrugge and Wolfgang. ADFs unify several generalizations of AFs, and it's possible to present different type of links between arguments beyond simple attack. And this is done by just adding a propositional formula to each argument. However, this further flexibility comes with the cost of further computational complexity for ADFs. I will return back to the formal definition of ADF in a few minutes. First, I want to talk about the motivation of this work. The notion of strongly admissible semantics for ADFs has been introduced, and several properties of this notion also studied. For instance, it is shown that each ADF has at least one strongly admissible interpretation. The set of strongly admissible interpretations make a lattice with the grounded interpretation as the top element and the trivial interpretation as the least element. Then the credulous decision problems under a strongly admissible interpretation, semantics, and grounded coincide. And also it is shown that the strongly admissible semantics can be the base for human-machine interaction that requires an explainable outcome. However, the computational complexity of under a strong admissibility semantics for ADF has not been studied yet. This was a motivation for us to analyze the reasoning task under these semantics and study the computational complexity of these reasoning tasks. I will present the meaning of each of these reasoning tasks later on, and I explain our results of computational complexity of each of these problems. In the following, first, I present a background about ADF, and I explain the notion of a strong admissible semantics for ADF. Then I go to the main part of our work, in which we present the problems, reasoning task problems, and we analyze the computational complexity of them. At the end, I will have a short summary of our work. And now I turn to present the notion of ADFs formally. Here, an ADF is a triple in which A is a set of arguments, L is a set of links, but meaning of links can be both support and attack, and neither of them. And to each argument, a propositional formula is attached that presents under which condition an argument can be accepted. For instance, here the acceptance condition of B says that B is acceptable if A is accepted and C is rejected. Semantics of ADFs usually presented by interpretations, and interpretation is a function that assigns each argument to true, false, or undecided. In our work, we sometimes choose this notion of presenting the interpretation in which we keep an argument as a positive literal if it's assigned to true, we keep it as a negative literal if it's assigned to false, and we doesn't present the arguments which are assigned to undecided. Truth values can be ordered via information ordering. We use this notation to present the, this notation means that we keep the truth value of all arguments in set P as it is in V, and we assign all the other arguments to undecided. This acceptance condition, this is a partial evaluation of the acceptance condition of argument A under interpretation V, in which we replace the parents, the truth value of parents of A. And the characteristic operator is a function that takes an interpretation and revise the information of interpretation V to V prime. Here we evaluate this acceptance condition. If it is irrefutable, then we assign A to true in V prime. If it is unsatisfiable, we assign it to false, and otherwise we keep it undecided. Now I'm going to present some of the semantics of ADFs. For instance, an interpretation is called admissible if it doesn't contain any unjustifiable information. That is, if an argument is assigned to true or false after applying the characteristic operator over V, we have to have the same truth value for those arguments. Here you see the set of all admissible interpretations of these ADFs, and the interpretation is called grounded if it is the least fixed point of this characteristic operator. It means that the grounded interpretation presents the minimum information about the truth value of arguments in a way that no one has any doubt on the truth value of those arguments. In this ADF, for instance, this interpretation that assigns D and C to false and A and B to true is the grounded interpretation. Assume that I am asked about the credulous decision problem of one argument in the grounded interpretation. Then the question is that, do we really need to construct the grounded interpretation, then answer the question, or is there any further way to answer the question? For instance, if we want to know whether D is assigned to false in the grounded interpretation of this ADF, we actually do not need to construct the whole grounded interpretation. We can check the acceptance condition of D, and since it is unsatisfiable everywhere, then we can say that, okay, D has to assign to false in the grounded extension. And if we want to know whether C has to assign to false in the grounded extension, again, we check the acceptance condition of C, and by the knowledge that D is assigned to false in the grounded extension, and by evaluating C partially under this truth value, we know that, okay, then C is also assigned to the grounded, to false in the grounded interpretation. Actually, a strongly admissible interpretation presents a minimal justification that is needed to answer whether arguments can be justified in the grounded interpretation or not. This is the idea of presenting the strongly admissible interpretations for ADFs. And here is the formal definition of a strongly admissible interpretation, which is defined based on the notion of a strongly justified arguments in a given ADF and in a given interpretation. If A is assigned to true, we want to check whether the truth value of A in this interpretation depends on a set of parents of these arguments excluding itself, such that each parent satisfies this property as well. It shows that the notion of a strongly justification is introduced recursively over the set of parents of each argument. If this is the case, we say that A is strongly acceptable, and if A is false and this property holds for A, we call it A is strongly deniable in this interpretation. And if we are not care about true or false in our work, we call it strongly justified in this interpretation. And in a given interpretation, if each argument satisfies this property, then we call that interpretation a strongly admissible interpretation of ADFs. This is the notion this is the notation that we use to show the set of all a strongly admissible interpretation of a given ADF. Back to our example, for example, if we want to show that whether this interpretation is a strongly admissible, we have to check whether C and D are strongly deniable in this interpretation. As we have already checked, this is the case for these two arguments. Therefore, this interpretation is a strongly admissible interpretation of these ADFs. And here is the set of all strongly admissible interpretations of this ADF. As you see, the grounded interpretation is one of them, and the trivial interpretation is also a strongly admissible interpretation, and it is always the case. Now I'm going to the main part of our works, in work in which we present the decision problems and we analyze their computational complexity. As the first decision problem, we presented the credulous decision problems for under these semantics, in which an ADF, an argument, and its truth value of that argument is a part of our input. If we can find a strongly admissible interpretation that satisfies this truth value for A, then we say the answer of this credulous decision problem is yes. It means that if there is a strongly admissible interpretation that in which A is strongly justified, and otherwise the answer would be no. We show that the computational complexity of this problem is co-MP complete for ADFs. And the reason is that, as I told, in any ADF, the grounded interpretation is the top strong admissible interpretation. Therefore, answering the credulous decision problem under strongly admissible interpretations and grounded semantics coincide, and we already know that this problem is a co-MP complete for ADF, then this problem is a co-MP as well. The second problem that we studied in our work is a skeptical decision problem. In this problem, we want to check whether A is assigned to X in all the strongly admissible interpretations of a given ADF. And since the trivial interpretation is the least strongly admissible interpretation, therefore, the answer for any ADF for any argument and any truth value would be no, then this problem is a trivial problem. Another decision problem that we introduce is a verification problem. As usual, we have an ADF and an interpretation. We want to check whether this interpretation is strongly admissible in these ADFs or not. If the answer is yes, then if there exists such an interpretation, then the answer is yes. We proved that this decision problem is a co-MP complete for ADFs. We show that this problem is a co-MP problem, and we show that it is co-MP hard. To show that it is co-MP problem, we proved by the complements of this problem. First, we proved that if we can find an interpretation that has a strictly less information that such that satisfy these two properties together, then interpretation B is not a strongly admissible interpretation. This guessing step takes NP time since we choose the interpretation non-deterministically. And this step of checking whether W satisfy these three characteristics takes polynomial time. Therefore, this when we reach to no problem, it takes it will be a NP problem. And when there is no such an interpretation, then it is a complement of that problem, and the computational complexity of this is a co-MP problem. For the hardness, we use the standard propositional logic problem of validity. We choose an arbitrary Boolean formula. We transfer it to an ADF for each literal in this Boolean formula. We add one argument in this ADF, and we add one extra and new arguments in this ADF. We introduce the acceptance condition of all the arguments that appears in this formula by X itself. And for the new arguments, we define the acceptance condition as psi. We prove that this psi is a valid formula if and only if the interpretation, if argument A is assigned to true, is a strongly admissible interpretation. And it shows that this problem is a complete hard. We introduced another computation, a reasoning task in our work, which we call it a strong justification problem. Here we want to check whether A is strongly justified in interpretation B or not. It is necessary that I mention that when we have an interpretation, for instance, here B is not a strongly admissible interpretation itself, but it contains C and D, which are assigned to false, and it is easy to check by the definition that these two are strongly deniable. And then this is different with this is a different between this reasoning task and actually credulous decision problem. We show that the computational complexity of this problem is a co-NP complete to show that it is a co-NP problem. We transfer this ADF to a new ADF. We constructed a new ADF based on the interpretation which was given. We added 2 new arguments and we changed the acceptance condition of arguments based on their truth value in the given interpretation. And we proved that this strong justification problem answers yes, if and only if this credulous decision problem undergrounded semantics for this new ADF is yes. And for the hardness, the hardness part is exactly the same as the verification problem. We choose a propositional formula, and we show that this decision problem answers yes, if and only if this psi is a valid formula. And as the last decision problem, we defined a smallest bitness of a strong justification. Here we have an ADF as an input, an argument, and its truth value. Further, we have a number k as a natural number k as an input of this decision problem. We want to decide whether there exists a strongly admissible interpretation that satisfies the truth value of A and assigns at most k number of arguments to true or false. This decision problem construct a kind of bound over for the strongly justification of argument A. We show that this problem is a sigma 2 problem. For this part, we guess about an interpretation and we check whether we satisfy these 3 properties. Guessing part can be done non-deterministically, then it would be NP. This one takes NP time. And the first item here is a verification problem. We already showed that this problem is a co-NP problem, and these 2 parts take polynomial time. Therefore, the computational complexity of the whole part will be increased to sigma 2. And for the hardness, we choose a quantified Boolean formula. We show it with big theta here, and we construct an ADF based on the literals which appears in this formula. We assign, we keep all the, for each proposition, for each variable in y and z, we define arguments. Further, were arguments for the one which appears as a negation of y. We also define a new argument y bar, and we also add one further argument for theta itself, which is a part of the this formula. And for the acceptance condition, we assign all the arguments of y and y bar to top. For the acceptance of z, we assign all of them to negation of z, and we replace all the negation of y in theta with y bar, and we prove that this decision problem answers yes, if and only if theta is a valid formula. And yeah, as a summary, in our work, we presented a reasoning task for a strongly admissible semantics of ADFs. We analyzed their computational complexity. We show that a credulous decision problem, verification problem, and strong justification problems are co-NP complete, and skeptical decision problems is a trivial problem. And we also shown that witness of a strongly justification of an argument is a sigma 2 complete. As usual, the complexity for ADF increases by 1 level when compared to ADFs in a hierarchy of, And we also shown that in compared the verification problem under grounded semantics of ADF is a DP complete. However, it is co-MP complete under strongly admissible. It shows that checking whether arguments are actually assigned to undecided in the grounded interpretation adds an NP part in the computational complexity of this problem. And as a future work, we are interested to analyze the complexity of this type of semantics for other generalizations of AFs, which are subclasses of ADFs. Thank you for your attention.